This is the core component mock at Holy Cross, and this is your paper 4, if you're lucky enough to do that. We are on question 1. And by means of a simple label diagram, indicate the structure of a triglyceride fat molecule. Detailed biochemical structure is not expected. So all we're looking for is that'll do. And labelled diagram. Label diagram. So I'm going to put some labels on this. I'm going to label that, and I'm going to label these. So that is what formerly was glycerol, and these are fatty acids. We didn't need to show all the carbons. I wasted time. It just said a simple label diagram to show that you know what a fat looks like. Name the bonding involved. You should know the name of the bond, just remembering. And give two differences between the structure you've drawn and a phospholipid. Well, a phospholipid would start off the same with our glycerol, and it would have two fatty acids, but then would have a phosphate or a phosphoric acid. So we would say only two. So two differences between the structure you have drawn and a phospholipid. So I'm going to talk about it from the structure we have drawn point of view. So triglyceride has 3 fatty acids. Phospholipid has 2 fatty acids. Triglyceride has no phosphate. Phospholipid has a phosphate. So I'm sure you can get away with just half of that sentence each time, but I've just put both just to show you that it could be done that way. And you could possibly, so we got our 2 marks there, but we could possibly suggest that now this phospholipid has got a hydrophilic head component and a hydrophobic tails, where the triglyceride has just got hydrophobic areas. So the triglyceride has only hydrophobic areas. Phospholipid has hydrophilic head. But we've gone for the first 2 simple marks there. Suggest one reason why animals tend to store energy in the form of fat rather than carbohydrate. Very simple. Fats have got higher energy. So fats have higher energy. With all of those hydrogens and carbons, if they respire aerobically, they'll give about twice the energy as carbohydrates. And so you only need to carry a lower mass of fat to get the same energy. You'd have to carry a lot more carbohydrate. What is the difference between a saturated and unsaturated? You don't need to draw these. but I'll draw them just so that you can see. So you've got, for example, a carbon chain there. This is, and the rest of the molecule there, this has got as many hydrogens on as is possible, so that is saturated. And if we draw a similar thing here, this might have a double bond there. And carbon can only make 4 bonds, so this one would have 4. This one, 1, 2, 3, can only have 1. 1, 2, 3, can only have 1. That one could have 4. So the unsaturated has got double bonds and not as much hydrogen. So we're going to say saturated has more hydrogen. So that's 1 mark, so that'd get us the mark there. And what other things could we have possibly have said? Well, we could have possibly suggested their state at room temperature. So saturated solid at room temperature, unsaturated is a liquid. We could have mentioned, we could have mentioned our double bonds. So single bonds in saturated, double bonds in unsaturated. We could have mentioned the shape of them as well, but there we go for a mark there. An experiment was carried out. Oh, it's a little bit dark. There we are. An experiment was carried out to find the effects of the enzyme. So we might have some enzyme information now. Lipase in the fat in milk. You've probably done this as a practical. We've got using full cream milk mixed with sodium carbonate solution and indicator, and it tells us the colour of the indicators there. So red, green, oh, I've even got a green colour there, and blue. And in tube A, so we got tubes A and B. In A we've got normal and unboiled, so just the enzyme. And in B we have got boiled and cooled enzyme. Okay. And then they stick in the milk, the sodium carbonate and the indicator solution in the rest. All the same. So the only difference between these two tubes is the difference between normal enzyme and boiled enzyme. Then they were incubated for a certain amount of time. Why did we add sodium carbonate? Well, sodium carbonate will raise our pH. It's an alkali, so our sodium carbonate is an alkali and will make our pH higher, or it'll go blue. So we just need to say make the contents of the tubes alkaline, or raises the pH. It's not in the mark scheme, but I would suggest the most important thing is it makes the colour different. So it makes the colour start at blue. So colour starts at blue. There's no point raising the pH if it doesn't change the colour. So I would certainly suggest that. What colour would you expect in tube A after 3 hours incubation? So that's got the enzyme there, and what's going to happen is, if we go back to our, I've lost it, there it is, go back to our lipid, and remember, if you can't think of what to say later on in a question, always go back and read it again, and you probably find the information is there. So this lipase is going to break these ester bonds, and we will then have separate glycerol and fatty acids. And surprise, surprise, a fatty acid is an acid, it's acidic. So now we have got the contents of this tube A have got acids in them. So that's going to lower the pH. And that's what's happened in the next experiment. So what colour would we expect? Red, possibly green, It'll go green then red, it depends how long it's been left for. 3 hours is enough. It depends how much lipid you put in. But red or possibly green. And briefly explain your answer. Well, the enzyme lipase, it splits that lipid up into its component parts, but we're going to use the posh word for that reaction. It hydrolyzes the lipids, or the fat in the milk, and the fatty acids lower the pH. It's a nice simple story there. Explain why no appreciable change in colour was observed in tube B. Strange word, that, appreciable. You can just read that as no change in colour. Appreciable means anything that you can notice. So in tube B we had boiled enzyme. Alright, okay, well if you boil an enzyme then it ain't going to work. So we just need to describe exactly what's going on there. So boiling has denatured the enzyme. I think someone's denatured this pen, it's running out of ink. There we are, get rid of that. Has denatured the enzyme, and we could say further, bonds are broken, changes the tertiary structure and so on. But the most important thing is it changes the shape of the active site. Any question that mentions an enzyme, odds on you're going to have to mention an active site somewhere. So, it's no longer complementary to the substrate, which in this case was milk fat. No enzyme substrate complexes, and so no fatty acids produced, and so you're going to get no acidic shift in the pH and no colour change. But that is a really common question in different forms, a really common experiment to ask about.